So hi, my name is Xinyuan, and I would like to talk about the research my team and I worked on this summer, where we evaluated the performance of double-pumped interconnect in coarse-grained reconfigurable arrays. So my research has to do with computer chips, and two of the longest-standing problems in the field of chip design are cost and speed. When it comes to custom chips, it is not uncommon for a minimum order to cost over $1 million. And as cost is almost directly proportional to the area of the chip, any reduction in chip size has the potential to save the manufacturer a large sum of money. The operating speed of the chip should also be kept as high as possible. You can make a laptop paper thin, but people won't be happy if it starts lagging. And as it is difficult to have both improvements at the same time, the problem of area versus speed has bothered chip makers for decades. And as CGRA is a type of computer chip, our research aims to decrease the area cost of a CGRA while keeping the operating speed as high as possible. So to be precise, a CGRA is a type of hardware that you can program. Typically, if you want a custom chip, you need to design it from scratch. A CGRA, on the other hand, provides you with a set of little calculators, the PEs in this diagram, and can allow you to create your own custom chip by changing the settings on these PEs. While their performance is typically a bit worse than full custom chips, you no longer need to hire an entire design team to make a single piece of hardware. The CGRA works by allowing the PEs in this diagram to talk to each other using interconnects, represented by the orange blobs on the right. And the goal of our research is to reduce the area cost of these interconnects. In a 2017 IEEE paper written by Stephen Chin, the interconnects in a CGRA can be shown to occupy over 20% of the overall chip area, making our attempts a meaningful effort at cost reduction. So let me explain our goal using an analogy. Imagine a highway used to connect parts of a city. People get on the highway so they can reach their destination, where they can then work, eat, or do whatever else they need to carry about their day. Note that people don't actually want to spend that much time on a highway, and cities don't want to be congested by them. Now, the interconnects of a CGRA are like a highway. Instead of transporting people, they transport signals so they can eventually reach their destination to do a computation. Like a highway, the interconnects don't actually allow signals to do useful work. However, they still take up space in the chip, and space is money. Now, you might be asking, since they're not doing any work, why not get rid of them? Well, it turns out that we can't, just like we can't yet with a highway. What we can do, however, is reduce their area cost as much as we can, and we do this through a method called double pumping. Double pumping interconnect is like turning a 4-lane highway into a 2-lane one. In order to allow the same number of people to reach their destination in time, cars need to travel at double the speed. And so we allow the interconnect to pump signals at double the speed. In order to accomplish this, we add components to the CGRA and evaluate them across different designs. We came up with 3 designs for our double pumping solution, and each of them performed differently in terms of area and speed. Our methodology leverages standard tools used in industry, and in essence, these steps are to model, simulate, compile, build, and trace. First, we need circuit models for our CGRA. Leveraging the CGRA-ME framework, we generate high-level architecture description files by telling the framework the type of computation we wish to perform and the type of architecture we wish to use. When we modify these files to incorporate double pumping, we now have a set of models to evaluate, the baseline versus our modified designs. Before we move on with our models, we simulate our results using ModelSim, where we check the resulting waveforms to see if our results are sensible. If the waveforms are correct, we can move on to step 3, where we synthesize our model. Synthesizing a circuit from a model is like creating a scenery from Lego blocks. Our model is the scenery, and the standard cells are the Lego blocks we have to work with. Using Synopsys Design Compiler, we turn our hardware models into a standard cell netlist, showing exactly which cells will be used to build our circuit. The standard cell netlists are then used by step 4, where we place our standard cells and wire it up using Cadence Innovus. Now we can see a chip forming, and we have our accurate circuit design. When we pass the final circuit information to Synopsys PrimeTime, we can trace the longest path in the circuit and find the maximum frequency at which it can operate. Here I have the results from one particular run case to show you the potential benefits of double pumping. These graphs show the area and frequency costs of our design. In this example, 2 of our designs provide a reduction in area and negligible speed cost. One can also choose to take a performance hit for even greater area reduction. To check the validity of our results, we collected area and timing numbers across a variety of CGRA interconnects, and you can see the consistent area reductions across all of them. higher area reduction is observed in CGRAs with more interconnect richness. And performance speed does not greatly change when double pumping using designs 2 and 3, shown with the shorter bars in this diagram. In conclusion, across the CGRA architectures we evaluated, double pumping can provide an average of 6% area reduction with no speed cost, an average of 10% area reduction at minus 32% speed, and in general, it can provide greater area reduction at higher interconnect richness. For producers who use CGRA or who would like to apply our strategy in other contexts, it means their product can cost a bit less and run a little bit faster. My team is currently in the process of evaluating double pumping designs across other CGRA architectures. And we are also working on a paper for the Design Automation and Test in Europe conference. Finally, future researchers can evaluate the performance of double pumping in other circuit designs, and chip designers continue in their endeavor to find cost-effective and fast-performing designs for the next generation. Thank you so much for listening, and I would like to open up the floor to questions.
Thank you for your presentation. Judges, feel free to unmute your mic and ask questions.
Okay. Something that I didn't really get much of a sense of from your presentation is exactly what your contribution to this overall project was. I mean, you kind of had a flow chart back in one of your earlier slides. Perhaps you could go back to that and kind of point out where your contribution to this work was. There, yeah. Like,
I was mostly working with the other 4 parts of this project. The model was built by previous students working on the team, and my goal was to add the components that do the double pumping and simulate to see if the results work. So when we had issues with our timing, I would go and debug the model sim results. And I actually went to Synopsys design compiler to compile the circuit down into the circuit elements. I went into Cadence Innovis to create the circuit and check the wiring and check the parasitic files. And I did the final path tracing to find the max delay in the circuit, the critical path delay, and to find the max frequency from that. But the circuit model was given to me, and I only had to modify it.
okay, thank you.
Thank you for the. My voice is echoing. Can you hear me well?
Yes.
Oh, I think you're muted.
Hello, does anyone have any other questions?
Did she get to ask her question? It seems like.
I think so. She got muted.
Okay.
Oh, I don't know. Can you hear me now?
Yes.
Oh.
Okay. So I just wanted to know the type of software that you use to do simulation.
Use Model Sim, Altera Model Sim.
Excuse me? I think my connection is not.
Maybe type the answer in the chat. That might be helpful. You're muted, Maisha.
Sorry. There's another question in the chat, which we have some time for you to answer that.
So the question is, why does Design 2 award a greater area reduction for lesser speed reductions compared to design 3. What were the key differences between these two designs? What is the size operating speed difference between these CGRA and standard chips? So between design 2 and 3 was that design 3 was actually a standard design that we saw from a textbook, and we wanted to show that in our paper to show that the most basic thing that you would immediately go to would be design 3. But however, it would offer less area reduction than design 2 did. And they both had similar speed costs. And essentially the difference between them was that for design 3, we used regular registers, whereas design 2 was using pulse latches that functioned as registers but took less area. And between I'm not sure what the second part of the question means, because CGRA is a type of chip, and I'm not sure what a standard chip is. I wouldn't be able to answer that.
All right. That's fine. We can move on to the next presentation.